When scientists say that an ancient eruption was a 7 out of 10, they're not talking about how many people it killed. They're giving it a VEI rating, a Volcanic Explosivity Index rating. This scale measures how big an eruption was based on things like how high its ash cloud reached and how far away it sent rocks and other stuff. And scientists use it to compare eruptions from all different volcanoes. But how do they get those numbers? It's a little complicated. Let's take a look. The Volcanic Explosivity Index, or VEI, was created by a guy named Chris Newhall in the 1980s. He wanted a way to compare the magnitude of volcanic eruptions so scientists could better understand their impacts and make better predictions for future ones. Since volcanoes don't blow up very often, especially not in populated areas, we have very little footage of most historic eruptions. So to figure out how big they were, researchers rely on ice cores, tree rings, and layers of sediment called tephra that build up in lakes. These help us piece together what happened during past eruptions and how big they were. Once scientists have gathered as much data as possible about an eruption, they can start figuring out its VEI rating. There are 8 different categories of the index, each representing a range of eruption magnitudes. The categories are numbered 0 through 8, but not every volcano will fall into these categories neatly. Some might be a 2 in some categories and a 3 in others. All the different measurements come together to give the eruption an overall VEI rating. To break down the VEI, let's look at one of the best documented historic eruptions, Mount St. Helens in the U.S. state of Washington. On May 18, 1980, this volcano blew up so violently it lowered the surrounding land and triggered the deadliest landslide in recorded history. Today, it is the most dangerous volcano in the country. Scientists know a lot about what happened there because it was recorded with instruments and cameras, and we have a lot of physical evidence of the damage it caused. That makes it a great example to walk through the VEI categories one by one and see how they work. VEI ratings are based on 4 different measurements of an eruption's explosivity. These are the volume of material ejected, the height of the eruption column, the width of the area covered by deposits, and the intensity of the eruption. Let's start with volume. The amount of material ejected during an eruption is measured in cubic kilometers or km cubed. It includes everything from ash to lava to rock fragments called tephra. Mount St. Helens ejected 1.6 cubic kilometers of material during its 1980 eruption. Depending on the size of the volcano, that could earn it anywhere from a 1 to a 4 on the VEI scale. The bigger the volcano, the more material it can eject without being a super big eruption. Scientists usually measure the volume of material ejected during an eruption by looking at the size of the crater left behind and the thickness of the layers of debris around it. Next, there's the height of the eruption column. This is how high the ash plume went above the volcano. For Mount St. Helens, the column was about 30 kilometers tall, which is about as high as 10 Mount St. Helens stacked on top of each other. The eruption column is made when gas and ash are blasted high into the air during an eruption. As the column rises, it cools and condenses just like water vapor turning into a cloud. In fact, you can tell a lot about an eruption just by looking at the shape of its column. Some are wide and short, others are narrow and tall. Most look like a mushroom cloud, wide at the top and narrow at the bottom. That's because the wind pushes the ash away as the column rises. Once it reaches the top of the atmosphere, though, the wind can't push it around anymore, so the column expands sideways. The height of the eruption column is important because it affects how far the ash and gases travel from the volcano. The taller the column, the higher the potential for danger. For this category, the height of the plume determines the VEI rating, which is why scientists use lots of different methods to measure it. Sometimes they use historical records, aerial photos, or satellite images. When those aren't available, they use geologic evidence such as the thickness of ash layers found at different distances from the volcano. These measurements can also be used to estimate how far the eruption cloud traveled after it reached the top of the atmosphere. Back to Mount St. Helens. Using all this information, scientists determined that its eruption column was about 30 kilometers high. That's enough to give it a VEI rating of 4 in this category. Another way scientists can determine the height of an eruption column is by measuring something called the eruption plume overshoot. This is how far above the volcano the top of the plume reaches. For Mount St. Helens, the overshoot was about 30 kilometers. But not all columns overshoot in the same way. Sometimes the overshoot happens gradually, like the top of a balloon floating upward. Other times, it happens suddenly, like when a balloon pops. In either case, the overshoot can provide important clues about the strength of the eruption. To calculate the overshoot, scientists typically use aerial photographs or video footage taken during or shortly after the eruption. So far, Mount St. Helens has earned a 1 to 4 in 2 of the 8 VEI categories. Remember, these categories range from 0 to 8, but the VEI doesn't just take into account the height of the eruption plume. It also looks at the width of the area covered by deposits, also known as the eruption radius. This is the total distance around the volcano where tephra was deposited. For Mount St. Helens, the eruption radius was 55 kilometers, earning the volcano a VEI rating of 5 in this category. Scientists usually measure the eruption radius by mapping the extent of the tephra deposits. They can also use aerial photographs, satellite images, or even topographic maps to help them do this. In some cases, scientists may need to use multiple methods to get a complete picture of the eruption radius. Finally, there's the intensity of the eruption. The intensity category is a little different from the other three. It takes into account both the energy released during the eruption and the explosivity, or how quickly that energy is released. A low-intensity eruption releases a lot of energy over a long period of time. A high-intensity eruption releases the same amount of energy very quickly. This category considers both the duration of the eruption and the size of the earthquake that occurs as a result. Long-lasting eruptions with small earthquakes are less intense than short, intense eruptions with large earthquakes. The duration of an eruption is how long the volcanic activity lasts. It can be measured in hours, days, or even years. For smaller volcanoes, a longer duration means a larger eruption. For larger volcanoes, a longer duration means a smaller eruption. An earthquake is when rocks underground suddenly shift, releasing energy in the form of seismic waves. Earthquakes are a natural part of the volcanic process. They happen when magma moves through the Earth's crust, or when rocks break apart due to pressure. The intensity of an eruption is important because it tells us how much energy was released during the eruption. It also gives us an idea of how explosive the eruption was. For Mount St. Helens, the eruption lasted for 9 days, including the initial blast and subsequent lava flows. The earthquake associated with the eruption had a magnitude of 5.1. Together, these measurements earn the volcano a VEI rating of 6 in the intensity category. Now we can put all the numbers together to get the overall VEI rating. Add up the numbers from each of the 4 categories and divide by 4 to get the average. Round to the nearest whole number and you get a VEI rating between 0 and 8. Mount St. Helens had a VEI rating of 5 for its 1980 eruption. But why stop there? You can actually calculate the VEI for pretty much any eruption in history. Grab a pen and paper and some data about your favorite eruption. Then follow the steps outlined by Newhall. Remember to consider the volume of material ejected, the height of the eruption column, the width of the area covered by deposits, and the intensity of the eruption. Once you've got all the numbers plugged in, add them up and divide by 4. Don't forget to round to the nearest whole number. And if you want to learn more about some of the biggest eruptions in history, check out our resources. Now go out there and decode some ancient eruptions. Who knows? You might just discover the next big thing in volcanology.